be nervous. I suppose we are live. There's a little preamble. They edit the episodes, so they make it sound much better. They take out little bits and pieces if they need to. But hello, everyone, especially to our live watchers. Will be joining us shortly, I'm sure. Yeah, this is the sort of beginning. Actually, I've got the music theme tune to play. So we'll have the theme music, and that's when we'll start the podcast. So everyone feel like we're ready to go?
Yes, sir.
I'm going to learn loads here, I think. So I'm excited. All right, let's do it.
Let's do it. It's go time.
Hello and welcome to Go Time. I'm Mat Ryer, and today we're talking about memory management. We're joined by distinguished engineer Bryan Boreham from Grafana. Hello, Bryan.
Hi there. Hi, Matt.
Welcome to Go Time.
Thank you for having me.
No, it's our pleasure. We're also joined today by Director of Engineering at Cockroach Labs. It's Jordan Lewis. Hello, Jordan.
Hi, everyone. Nice to see you over this video.
Yeah, good. Thank you. I like the way you said that in a very sort of natural and authentic way. We also have my friend and yours, John Calhoun. Hello, John.
Hey, Matt. How are you?
I'm good, mate. Welcome back. It's been a while. How are you doing?
It has been a while since we've done this together.
That's right. Yeah, you were on it last week, wasn't you? It's welcome back to me, if anything. Do you want to say it or?
Oh, welcome back, Matt.
Oh,
sorry.
Thank you. Yeah, no, thanks.
I figure if you're hosting, I'll just kind of let you pretend like you've been here.
Yeah, fair play. Okay, well, I also like to do this little regular slot where I do a shout at or a shout out to a Go meetup from around the community. Today we are shouting at the Utah Go user group and Women Who Go Utah. Great groups there. Mariah Peterson tweeted that one at me, so you've been shouted at now. And if you're in that area and when you can, check them out. Go and join them in. Go and join in with them. Okay, I'm interested in this subject a lot because it's kind of like one of those ones that I think it has lots of interesting corners, but I think also there's having a good understanding of what's really going on can only help us. Maybe we could start with a little bit of history. What was memory management like in sort of programming languages before Go?
Yeah, good. Takes me back really because I have programmed in C and C++ and a few other things, and I mean basically. In C, you call malloc when you want some memory, and you call free when you want to give it back. You can have things on the stack if you don't want to do that, and those are your options. And so memory leaks, where you just forgot to free things, were very common. Memory overwrites, where you didn't realize that someone else wanted that memory, also happen. Pretty hard to get it absolutely perfect.
Yeah, it's funny, isn't it? Like, because you think in the simple case that's quite easy. You're going to ask for some memory, use it, and then give it back. But of course, like as soon as you have anything a little bit more complicated, that becomes a nightmare, doesn't it?
I feel like anybody who sorry, I was going to say I feel like anybody who's tried to teach with that style of programming should pretty quickly realize that even the simple case is not simple to somebody who's not used to it.
Yeah.
Yeah, I was going to say you get into things like reference counting, where you try and keep track of how many different things in your program want the same piece of memory. and when you count down to 0, now you can free it.
Right.
And used to do that by hand on iOS programming. It's got a little bit more automated since then.
Yeah,
but yeah, it's always a bit of a challenge.
Yeah, I had that same thing. So I kind of started in languages where memory was managed, actually, like scripting languages and C#, languages like that. And then I wanted to do something for iOS, and so I learned Objective-C. And this was before the ARC, the ARC, automatic reference counting that you're talking about. Before that, where you had to do the allocations and things yourself, and it is hard. You definitely end up relying a lot on the tooling to sort of, you use the app in the simulator and watch the memory for if it's leaking where it shouldn't and things like that. So, but yeah, it was so nice when that ARC stuff came out, and suddenly you just didn't have to kind of worry about that now. I think it was just the compiler, wasn't it? It was just would do it for you. It was checking where things were used and where they could possibly be used. And when they sort of fall out of scope, then maybe they could be cleaned up. It's but yeah, so we kind of take it for granted. Go has always had this, hasn't it?
I was going to say, I feel like I'm remaining quiet because my whole professional career, I've only used languages with garbage collection. I did a little bit of manual memory management stuff in school, and it was hard. And it didn't matter as much. That was kind of the great thing about it. You could get it a little bit wrong, and since it was just an academic project, it didn't matter too much. I didn't want to be the first one to mention the word lifetime, but for me, whatever you do with memory management, whether it's a language that has a lifetime kind of thing in it or not, it's all about thinking about those object lifetimes. That's what it comes down to, memory managed or not, right?
Yeah, so maybe you can elaborate a little bit on that then. For Go, when in Go, in the context of Go, if we have just a very simple case, we're going to have a function, we're going to declare a variable inside that function, we're going to assign that to a value, going to give it a value, and maybe then we're going to print it out, and then we're going to return. We're not going to return it. We're just going to leave it. What's going on in that? What's being allocated there for us, and when does that happen?
I thought you were going to carry on, Jordan.
Oh, that was short. Yeah. So it really depends on, I think it kind of depends on what the function you're calling is, right? I think in some cases, depending on what that function needs to do with the object that you're passing it, you may or may not be able to simply allocate it on the stack. You might be able to not have to use any kind of malloc at all, and just let it live on the stack, get passed to this thing, and get freed by the stack magic freeness of the world. If the function is doing something more complicated, if it has to store it somewhere, or it is more, if it's not even storing it anywhere, but the compiler can't infer that it's not storing anywhere, it might actually cause the code that's generated for that function call to require that the object that you've allocated gets promoted to the heap, which is kind of where the story begins.
Yeah. It's very interesting.
It does very quickly get complicated, doesn't it? The like for someone like me who's spent decades trying to both understand what's going on and make it go faster, usually, kind of understand all the ins and outs. But if you're as a beginner to all this, it's it just kind of looks like a variable. What are we talking about? So I think the two things, the stack and the heap, every Go routine has a stack, and mostly your local variables, things that you do in the course of a function, will live on the stack. And it's very, very fast, because as you come into a function, we just kind of add. We say the compiler figures it out. Compiler figures out this function is going to need 70 bytes of variables, so it just adds to a number, which is the stack pointer, and then we use that 70 bytes. We're using that for local storage, local variables. You come out of the function, you subtract 70. I'm sorry, trying to keep track of my own example. So you're just adding and subtracting, as you call more functions, you add more, and as you return from functions, you subtract. And the stack is a really fast and simple thing, but that's all you can do, and that's why what Jordan talked about, lifetime, comes into it. If you need a piece of data to hang around while you go call a bunch of other things, or you're going to keep that data and pass it between different Go routines, or you're going to cache it for the entire life of your program, that needs to live somewhere else. That can't live on the stack of one Go routine. So we put it in this other place, which goes by the name Heap. Heap as in just like a big old heap of stuff. It doesn't mean anything particularly technical. It's just the word that we use for the way that those longer lived, or at least might be very short lived, but we don't know for sure. So we put it on the heap, and then it can live for a long time.
Yeah. So do you need to know about this in order to write Go programs?
I would say not. I would say that is part of the magic of Go. That's the intention of the authors, that you just write variables and you pass them around, and you can do things that are a complete nightmare in C. You can return the address of a local variable from a function. That's a pretty much an instant crash in C. If it's not an instant crash, then it's a really weird bug. But it's one of those ones that will take weeks to find if it doesn't crash instantly. But yeah, so Go certainly makes it look easy, I would say.
I would agree with that. To me, it feels like Go, it really is trying to be a language where you can not have to think about any of these details if you don't want to. But if you want to, it also gives you some of the predictability, I would say, that you would expect from a language that is doing sane stuff using a stack and a heap kind of thing. You can, for the most part, predict when something is going to live on the stack versus something that's going to live on the heap. And that can really help you when working on problems that require performance. I think one thing that's kind of interesting is what is the line between needing to not having to know about the stack and the heap versus needing or not needing to know about, say, pointers versus values. That's something that I think trips up a lot of Go newcomers, especially ones that are coming from languages like maybe Python, where you're really not thinking about this stuff at all. But I think that's a little bit of an interesting choice. Exposing the detail about pointers versus values, and not really thinking so much about stack versus heap.
So how do you decide then, just for anyone listening, how do you make the decision about whether you're going to use a pointer or use the value? And we should say, like, for the difference, like, for example, if you've got a function that takes a pointer, you're literally just passing in a reference to something else, which is obviously a fixed size. Whereas you could be pointing to either big data, or maybe you just don't know, and so you want to be safe. Or you pass it without it being a pointer type, and you then are copying the entire value into the stack, right, of the new thing. So what's the consideration that you make when it comes to that?
I feel like there's a lot of them. It's pretty. I think this is one of the most tough things that people struggle with right when they're switching to Go. It's like, what is the algorithm that you're supposed to use in your head for choosing one of these things? There's certain things that are definitely constant. I'll name one of them, which is that if you have an object that has a method on it, or I guess we call it receivers in Go, if that method is going to edit the object, that cannot be a value receiver of an object. That has to be a pointer receiver, or else you're going to become pretty sad. You're going to run this method and it's going to edit, it's going to say, object.attribute equals blah, the thing will return. And then you'll be extremely confused because the attribute of some object that you pass will have never been edited, since really you're just examining and changing a copy of that value. I'd say that's a number one pitfall that I think even I've made mistakes like that, and I've been programming in Go for about 5 years now.
Yeah, no, absolutely. So that I like that one. That is like of course if you're passing a pointer to an object, then it's able to make changes to it. This is basically what you were saying in the analogy of taking in an argument there. And of course, if it's a value, it's a copy, so you can't. So that also communicates something to the user of your API, doesn't it, as well? If you have an API, and I mean, you can use it as an opportunity where maybe you've got a mix of these methods or functions, and some of them are going to modify and some aren't. Would you use that pointer as a sort of signal to that?
If I recall correctly, I think some of the Go style guidelines kind of suggest that if you use pointers for some of your methods, that generally you should use them for all, just for consistency's sake. Which, I mean, I get what you're saying, but I think the other side of the argument is that if it's not all consistent, it just could lead to some weird code to manage and read.
They'd rather just keep it simple, keep it all the same. Yeah,
I believe that's what it was. I'd have to go look again because it's been a while since I've read wherever that was.
Yeah. We've talked a lot about other languages and say C++. You have this const word you can put, so you can explicitly say whether the program's supposed to be able to modify this thing or not by the absence or presence of the word const.
And you can do that
Go
on
doesn't
anything,
have that, so.
Can you do that on any variable, on any object type? Because in Go, we're sort of more limited, aren't we, with our consts?
Yeah. Well, in Go, a const is a something like 3.14. The value of pi could be it's a constant. It's that kind of constant, a constant of the universe or a constant of your program. But in C++, the word const can appear as a modifier on anything.
I see.
Anyway, we're talking about Go here because it's the Go time.
Yeah, save that for C++
time. So yeah, it's a little bit that certainly if there's no pointer on a variable, then you get a copy of it. You do not get to modify the original. Well, I say that, but it's confusing because something like a map is inherently pointer-like. That's what the way I say it. That if someone hands you a map in Go and you make a change to it, add something to the map, you've added it to the original. The whole, and it kind of makes sense because the map might have 1,000 things in it. You don't want the Go runtime to go copying 1,000 things every time you pass a map to a function. But it is, I think, you kind of build up this set of rules you have to remember, like an int or a struct. It's going to copy if I pass the thing by value. A map is inherently pointer-like. A slice is kind of in between because I get given a value of a slice. I can write into the elements of the slice, but I can't change the length of the original. I can change the length of my copy. And these are I think mildly confusing parts of Go.
Yeah, they are. But as you sort of iterated them out, then I realized that it doesn't come up often. Like, I suppose because now I'm just second nature. I know if you're passing a map around, it's a map pointer essentially. But I'm sure there will be cases where that matters. But this comes back to kind of, for me, dead simple designs, really obvious, not trying to do anything clever. If you're taking slices and you're going to modify them, that sounds a little bit magic. I'd rather get them through a return argument kind of thing. So I don't know if I avoid it through that reason, but it is interesting, these things. And what about the size thing? You mentioned a map with 1,000 items. If you have a struct and it's just this great big object and it's got some image data in there maybe, and you know what I mean, it feels like a big thing. Is that enough of a reason to decide to pass it by a pointer always, just by default?
I'd say as a heuristic, if we're talking about, well, I guess I'm trying to figure out how your example works. So your example says you're holding a map that contains a big byte slice or something like that.
I just mean a struct, your own type, but it's got a lot of. You consider it big.
I see.
So but maybe it makes sense in your API that you don't have a pointer because you're not going to be modifying this, so you want to pass it in. But do you get a performance penalty if it's copying all that data into the...
You definitely do, and I think there's a judgment call about what's that threshold. Like when is it worth it to allocate and pass this thing by pointer? And we haven't even really talked about the performance costs of allocation really just yet. I'm sure that will come up soon, but definitely there's, depending on your program to some extent, and probably there's some rule of thumb that says maybe if it's, I don't know, more than what would your thresholds be, like 64 bytes, 32 bytes or something like that? I don't really know.
Well, I can guarantee it'll change from one CPU to another, and probably from one type of memory chip to another. It'll there's no one constant number where it's going to pass that threshold of whether it's cheaper to copy or cheaper to pass the pointer. But modern CPUs are amazingly fast at copying memory. I bet that number is bigger than you might have guessed if you haven't actively gone out and measured it.
Yeah, that's an interesting point. And you also mentioned measuring it, and I think that's another quite important piece. Is it's nice to write efficient code, but you can worry about it too much, I think, and sometimes it doesn't matter. And but I don't want to ever discourage people from learning more about that because it is very interesting. There's other little patterns as well that I think we may come up. Well, okay, so let's talk about the performance of allocating memory then. Of course, it's not a free thing to do, but it sort of feels like we are just reserving the memory, not that there's like effort to reserve that memory. What is the
do remember it's nearly free on the stack. It's when we do this lifetime management and we want it to hang around for longer. That's when the cost goes up.
Yeah,
I think that one of the most interesting things to me about doing performance measurement of simple things, because that's what we really love to do as programmers. We're like, well, let's try to figure out like what's the fastest possible way that we can write this like fairly simple algorithm that just does a couple of things, right? So we love to do that. We love to write a micro benchmark. Go's micro benchmark support is excellent. It's got all these different facilities, and there's bench stat, and you can like profile things up the wazoo, et cetera. One thing that I find very interesting, and that's kind of bitten me several times, is that if you just take a look at a CPU profile of a little micro benchmark that does a bunch of allocating, it's going to seem really cheap. Those allocations are really fast because the garbage collector is really good when the computer isn't under load and when there isn't like GC pressure, right? When the garbage collector isn't too taxed, it's going to be very cheap to allocate, and the garbage collection is going to happen in the background, and everybody's going to be pretty happy. What I've seen over and over again is underestimating the effects of doing a lot of allocations based on like in a real program, kind of micro benchmark versus real program. In a real program, those allocations are almost always going to add up to be more than what it seems like in your micro benchmark.
Yeah. I think it might be useful to try and motivate, think for a bit about what is hard about managing this thing we call a heap. So first of all, what is it, right? So you've got some random program. It's allocated a bunch of small blocks, maybe 8 bytes. It's allocated some bigger blocks, maybe some 64K blocks, maybe one block of 103,402 bytes. And the memory manager, the heap manager, has to let you do all of these things and do them in any quantities, in any order, and within some bounds, right? Your whole computer has got, 64 gigs of RAM, 16 gigs of RAM. There's some limit that you can't go above, but the heap manager will let you allocate any number of blocks of any size within that overall limit. And then it will let you free them up, stop using them. In Go, you don't explicitly do that. You just, when you no longer have any references to a particular piece of memory, then that's considered free. Well, it's considered garbage to begin with. It's still kind of hanging around. We'll get to that in a second. But assuming we've managed to free up some memory, now the manager has, next time you want to allocate some memory, it's got the task of figuring out where there's a hole, because you don't want to just get bigger and bigger and bigger the whole time. You've allocated 64K, you freed 64K, now you want to allocate 64K, you should probably use the one you just freed. So the memory manager has a task of trying to give you back the best block to keep things under control. Maybe not the best, but some kind of reasonable choice of block. It's got a lot of options, right? If you freed up 64K and then you allocated 8 bytes, well, it could take the first 8 bytes of that 64K. And I'm trying to kind of motivate this picture that it's actually really complicated to keep track of all these potentially millions and millions of blocks at all different sizes. Then we throw in some performance considerations that if most computers these days have multiple CPU cores, and you really want to keep the memory together on one CPU core and not kind of have little bits of memory next to each other being used by different CPU cores. So the memory manager is going to try and help that along. It's going to actually keep different, typically called arenas of memory for different cores. And we haven't even got to our garbage collection yet, right? It's already really complicated. And any memory manager in C, in C++, in Objective-C with your automated reference counting, they're all doing the stuff I've talked about so far. They're all kind of keeping track of what's in use, what's not in use, what could be reused. They're all doing that. I'm going to pause for breath now.
Stop the world.
Well.
Well,
yeah.
So,
shall we get into garbage collection?
Yeah.
Sorry,
So
John,
I was going to say, yeah, I was going to say, the reason why you can be relatively proficient at Go and not worry too much about what's going on underneath, although Bryan, that was a good example of a case where when you do know what's going on, you might make different design decisions. But the reason is really because Go has this garbage collector in there that's kind of freeing up the memory in our wake as we just sort of plow through our program. Tell us about the Go garbage collector. Is it good?
Yeah, well, it's pretty good. I mean, I think reasonable people can have vicious arguments about this, but
I'm sure they don't.
Yeah, so garbage collection as a computing technique has got to be 50, 60 years old.
Wow.
Lot of work has gone into it since the early Lisp days, and so the Go garbage collector is not state of the art, right? It's kind of a couple of steps back from that, but it is very, very effective. I'm pretty sure I could go there. The exact nuances of which techniques it uses and doesn't use. There's a great paper. We should put a link in the show notes. There was, I think, a keynote speech at a conference where somebody went through the entire history of the Go garbage collector and spoke about that they had actually tried out a lot of these more cutting edge techniques and the difficulties they had fitting them into the kind of world of Go. Well, I think we kind of skipped ahead slightly, haven't we? I mean, what is garbage collection? We talked about it in vague terms. This idea that once you no longer have any reference to a piece of memory, that it's considered garbage, and so what you want to do is identify all the garbage and then make it available for reuse as your program carries on trying to allocate more memory. And these days in Go, it's running Go routines in the background, kind of walking across the heap and doing this process of figuring out what's in use, what's not in use. It needs to figure this out starting from all the places you can start in your program. So that's, you can start from a global variable that could be a pointer to some memory. It could be a local variable on the stack of a Go routine. And anything that they point to, anything that those things point to, all of that, there's some way to reach a lot of memory, and that's the not garbage. And it has to work out what is garbage, which is everything else. And so yeah, it runs along in the background. So it doesn't stop the world. This used to be a big thing in Go. It used to kind of halt everything and then figure out where the garbage is and then carry on. And that's a bit annoying if you're trying to have a very interactive program. Something that's serving requests very, very quickly. It would stop for 100 milliseconds or something like that, and that's jarring if you're trying to interact with it. So it does most of the work in the background, figuring out what the garbage is. And then there's a very, very brief pause where it does still stop the world, but it stops it for, I don't know, 1/10 of a millisecond or something like that, and resets a few pointers and then carry on. Now you can carry on allocating memory, running your program, and so on. So that's basically how the Go garbage collector works. It does all of this in one heap, so it doesn't have what's called a generational design. It doesn't try and separate out younger lived things and longer lived things. It's not a copying garbage collector, which can be nice if you sort of take all the non-garbage and kind of copy it all the way down into one end of memory that's all together, and the cache works better that way. And then you start fresh in the kind of the big expanse that you've just moved everything. A lot of garbage collectors work that way. The Go garbage collector leaves everything where it is, never moves memory on your behalf. So that has pros and cons. And I think that's kind of the up to a certain level exactly how the Go garbage collector works these days.
I like how you describe it in terms of what it's not. I think that's a very effective way. It's hard to describe something in terms of what it is, especially something that's so complicated as a garbage collector.
Oh yeah. It's viciously complicated and really hard to get right. And I certainly take my hat off figuratively to the authors of the Go garbage collector.
Absolutely. My colleagues like to remind me that even though the Go garbage collector is not a moving collector, I think the spec for Go allows it to be a moving collector. Which is kind of interesting. No doubt, despite the fact that the spec allows this, it would break untold numbers of programs that use unsafe pointer and things like that. But I always thought that was kind of a neat loophole for the future that the Go team left.
Yeah, interesting.
Yeah, well, it's funny we talk about this idea that our garbage is going to be collected for us. And Brian, you mentioned a scenario earlier where you have a block of 64K and you free it, and then you get another one immediately, and you free that, and then you get another one. Why not just hold on to the one that you already had? And this is the concept of kind of using pools, which you can use. There's a pool in the standard library, the sync pool, which sounds cool.
Yeah. Well, I like to appeal to the song that goes reduce, reuse, recycle. At this point, that well, first of all, if you reduce the amount of memory you're using, then there's going to be less work for the garbage collector. But if you can reuse memory, like you were just saying with the pool, then again, the garbage collector has less work to do. And then finally, I guess recycle is what the garbage collector does. So
yeah, I like that. That's a great analogy.
Also seen cases where people try to do that on their own. I thought we had one episode with somebody who talked about channels and passing, I think, byte slices into the channels. Do you remember that, Matt? I don't remember
No.
which episode it was.
Yeah, I don't remember that, but yes, actually, well, let's talk about just quickly what a pool is, because it sounds really like cool and clever. It's actually quite simple, isn't it? Anyone can tell us about what a pool is now, if you like. Or
I was going to let Jordan take that one. Or...
Jordan, what's a
Sure.
pool for people? Who
Well, I can tell you a little bit about what a pool is. I don't know so much about how it works under the hood, to be perfectly honest, but the general idea of an object pool is that it allows you to reuse big and complicated and expensive to create objects by you ask for one of these big and complicated and difficult to create objects, you fill it out, you use it for a little while, and then when you're done with it, instead of just giving it back to the garbage collector to chop apart and throw back into the heap, you have a little moment in which, well, I guess you don't have to have this, but you can have a little moment in which you can clear it out and get rid of any other references in there or do whatever you want with it, and then stick it back into the pool for later use. And the purpose of this is really just to amortize the amount of work that you have to do to make one of these big things in the first place. And this can come into play in a lot of different scenarios. I think in Go, I mean, people love to use Go for like microservices. So for maybe a web service or some like RPC service or something like that. And a lot of the time you can imagine, an RPC service is sitting around idle maybe, or it's doing a bunch of work and then it's doing very little. And every time that it gets one of some request, it has to do some complicated thing and make a big object and do a bunch of like initialization work. And with an object pool, if you don't mind using some memory for a big cache of these objects, basically, you can skip a bunch of that initialization work, and that can really be nice. You can see improvements in your overall program's performance, depending on how expensive that initialization really is. I think that's basically the summary of an object pool.
Yeah.
It's probably worth noting that sometimes it's not even big objects, it's just things that are slow to set up. So like a database connection pool is pretty common to the database every single time you're talking to it. But if you have like a pool of connections that you can just take and use, then every single request isn't going to have that delay of connecting to the database and making sure it's all good.
I would add one thing to that, which is when you are, well, we didn't particularly talk about the performance angle, but the garbage collection does take a lot of work. It's work that mostly happens in the background, but it's undeniable. It takes a lot of work to kind of walk through all the blocks of memory that have been allocated and freed and figure out which is garbage and so on. It takes a lot of work. So the thing about big objects is that Go has a level, a number, which is the limit that it's going to let the heap grow up to. And it's a dynamic number. Go tries to sort of figure out what's the best number for your program. But let's say it's a gigabyte in your program's running along, it's doing a lot of stuff. And you're using memory, you're discarding memory, and the total amount of memory that is in play, if you like, will grow up to 1 gigabyte, because that's what I decided the limit was for this example. When it hits 1 gigabyte, now Go has to definitely figure out what's garbage, what's not garbage, because that's the sort of target it set itself. We call it a full garbage collector, a full GC. It's there's stuff going on in the background. It can kind of reclaim stuff as it goes, but when you hit that limit, it has to do a full sweep and kind of know exactly where everything is. And one reason for that is it's going to make a decision. If it genuinely can't get any more free garbage, it's going to go to the operating system and ask for more memory. At this point, it's probably going to go to 2 gigabytes. And going to the operating system from memory is a relatively very expensive thing to do. So Go is trying to keep to that limit that it previously chose. So back at the question of large objects, simply by allocating, like let's say you allocate 10 megabytes, you can only do that 100 times before you hit the gigabyte, right? Just in simple terms. So every 100 times you go through that bit of code that allocates 10 megabytes and then discards it, turns it into garbage, you're gonna hit a full garbage collect every time you hit that threshold. And full garbage collects are, in simple terms, I'm simplifying because it's horrendously complicated under the hood. In simple terms, you want to cut down the number of times you do a full garbage collect and the rate at which you do a full garbage collect. And so just for that reason, any kind of relatively large buffers, blocks of memory, you may want to pool. Not because they actually cost a lot to set up, but because they drive that number. So that's kind of a like a subtle piece of knowledge that you might not pick up.
Yeah, I would say. And how do you know if you're in that situation then? Is this back to you measure things? And so how do we do that? Like, what's the best way to measure this stuff?
Well, it's really about it's about setting up application metrics and paying attention to the sort of things that you have access to as a Go program. I think you can get some pretty detailed information about what the garbage collector and the heap is up to as a Go program by sort of asking the runtime. There's a special function that you can call, and it gives you back a bunch of information. So, you can kind of do this at a low level, but there's a lot of libraries out there that kind of have figured out how to piece this stuff apart and expose it as metrics, maybe as Prometheus or as a little web service or something like that. So you don't have to go through the pain of figuring out, what of these, I don't know, there's a lot of metrics in there, to be honest. There's like 50, something like that, 50 little different struct members that all have subtle different meanings that are important. But I think as just a basic idea of what's going on in the heap, I really like this program called StatsViz, which somebody named ARL made, that just exposes this little HTTP server that has a little kind of real-time drawn graph of the different lines. Like that threshold that Bryan mentioned is represented very clearly, and you can kind of see it's really neat. If you're running it on an active web server, you can see the actual amount of heap kind of trending towards that threshold. And as soon as it comes above, then you can see there's a line for the full GC. The thing drops back down again. The idle changes. It's actually very fascinating, especially both for just learning about how garbage collection works in general, as well as understanding the behavior of your program.
Great. Yeah, that tool looks great. We'll put a link to it in the show notes for sure. So yes.
So I work a lot with Prometheus. A lot of the Prometheus maintainers work at Grafana Labs, and so that tends to be my go-to technique for looking at what's going on, particularly at scale. If you've got 100 programs running and you kind of want to keep an eye on what the bulk of them are doing. So it's basically the same data. It's coming out of the Go runtime, but the they show up as things named things like go _ memstats _ heap _ alloc _ bytes. So that's like one of the core ones. That's how much memory has been allocated, and that's if it's going reasonably slowly, you can see that number rising. It typically looks like a sawtooth, right? It rises quite slowly, then it drops very sharply when we free everything up in that full garbage collect, and then it rises again. And what might be happening in your program might be garbage collecting like 10 times a second, in which case the metrics are not going to pick that up. It's just like a blur. And unless it's a really, really, really small program, you do not want the garbage collector to be running 10 times a second. Like once a second is more moderate, or or once every 30 seconds or something like that is gonna, it's a trade-off, right? The trading off how much memory you've got against how much work you want the garbage collector to do, against how big is your program. There's no kind of hard and fast rule. Well, there's one hard rule. If you're doing garbage collection, Go will run it the full garbage collect every 2 minutes. That's the slowest it will go. That's hard coded into the runtime. But yeah, if you watch the rate at which garbage collections are happening, which is a Prometheus metric, if you're doing it that way, I've forgotten the name. But if you watch the rate at which it's happening, I think a lot faster than 1 a second is probably too fast, and you can't really go too slow, because it you really run out of memory, or you'll hit that 2-minute point.
I didn't know about that 2-minute point. That's actually pretty interesting. That's like that's a trivia question right there.
Yeah.
One thing I wanted to actually quickly mention, just to tie this back into the object pool question, I think that there's something neat that happens, isn't there? When there's pressure on the Go heap, doesn't something special happen to the object pools? Don't they notice and maybe drop unused objects or something like that? I'm never exactly sure how that works, but I bet one of you know.
Yeah, there's a kind of secret tie-in between the garbage collector and the. So the pool we're talking about is in the sync package in the Go standard runtime, standard library. So sync.pool will, I mean, the way it kind of looks like it works is you get things out and you put things back. But sort of under the hood, it's got a secret tie-in with the garbage collector, just as you say. And depending on how things are going, the pool might shrink a bit in order to free up memory for the garbage collector.
I didn't know that.
Yeah, another good trivia question.
Yeah, yeah. You have to go to a very specific kind of pub where these are the sorts of questions. But when they come up, you're going to look. I mean, you're going to look great, aren't you?
I just thought it was every pub in San Francisco.
Yeah, it could be. Yeah. So with this garbage collector cleaning up after us all the way, that means we can't have a memory leak, doesn't it?
Ha 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 ha. We all laugh somberly.
Sad face emoji. What do you mean?
Well, there's a lot of different ways in which you can have a memory leak, even in a garbage collected language. I think that one of my favorite memory leak stories or types, I guess, has to do with these sync pools. So not to hammer the sync pool to death, but imagine what happens if you have one of these objects that's a little bit complicated, right? Maybe it's big, maybe it's small, but maybe it's a struct and it's got some slice pointers. And maybe you're actually like slicing the front off of those slice pointers little by little, because you're implementing a queue or something, whatever it is that we do when we slice off the heads of our slice pointers. As it turns out, the garbage collector cannot free the front half of slices. If you take off the first 5 elements of a slice and then you don't change what that slice is pointing to, that array never changes, let's say, those first 5 elements will stay on the heap forever. And let's say that they actually are pointers to some other giant objects, then those objects are basically lost, and you'll never really know. You can get into really, really bad territory with stuff like that. And that's happened to me several times working on CockroachDB, which is this big Go program that has a lot of tricky stuff to deal with memory.
Yeah, that's one that I've seen myself, because I was trying to teach people how to use a queue or how to write a queue in Go. And like the simple implementation, you want to do that, but then you also have to like have the caveat of like, if this goes long enough, it's eventually going to break, because you're just going to indefinitely keep using memory. So it's like hard, because you're like, I want to show you the simple version, but I also don't want you to have something in your code that potentially is going to be problematic. But there's also like another case where that happens is when you have like Go routines that just don't end for some reason. And like time.tick is an example of that, where it's a function you call in the time package that when you call it, it gives you a channel that will send a message every so often. So it's supposed to tick every second or whatever time you want.
Yeah.
And like it actually has explicit documentation that this won't be garbage collected And there's ways to do it with garbage collection, but that specific helper, there's just not a way to clean it up.
That's so strange.
So
why is that thing? Why is that slicing the heads off thing? By the way, I like how you described that. You sound like a murderer. But what is that thing? Like, why does it do that? The first 5? That seems such a random thing. And is it not fixable?
Basically, the reason for that is that a slice, right? As we know, it's got a little bit of information about the length. That's the slice header, and it's got an array pointer. That's what makes up the data inside of the slice. And as I understand, once you've like created the array that has the data in it, you can't exactly say to the garbage collector that this array of a particular size is like half collectible, or you're just not allowed to do that. That's based on how the implementation of the garbage collector kind of works. It probably gets into things like size classes, right? When you're allocating objects of a certain size, I think the allocator likes to give you chunks off of a particular area that's all doing chunks of a certain size. So if you were to maybe edit the size of an object that's already been allocated, probably something would get confused and etc. I bet this is fixable. I don't think that it's something that's hard and fast, impossible to fix, but I doubt that it would be fixed soon, just because I don't think it's the most important thing to improve in the Go language right now.
I see. Well,
yeah,
sorry, Brian.
You can have pointers into the middle of an object, whether it's a slice or a struct or whatever, and that's kind of part of the picture. The way things are, any number of pointers, in whether they're at the beginning or into the middle of a single object, keeps it alive, keeps it from being turned into garbage.
That makes sense, I guess, doesn't it? You'd be surprised if it wasn't the case, would you?
Well, I think Jordan's example, you could construct a kind of proof acceptable by humans that nobody could ever get to the beginning of this slice. But the as he was saying, the garbage collector doesn't have sufficient information about what's inside objects that would allow it to break it in half or whatever.
Yeah, I see.
So I was going to say, the word leak, when I first programmed in C, a memory leak was when you had lost all reference to a block of memory, and you would do that quite a lot, so it was just leak the memory. You could never get back to it, you could never free it, and it just kind of hung around because there was no garbage collector in C. In garbage collected environments, we use the same word, a leak, but we pretty much mean memory which we do still have a reference to. Something is still keeping it alive, but we didn't mean to. It's hanging around. We don't actually have a purpose for it. It's hanging around because we've got a reference to it, but we didn't mean to have a reference to it. So that's it's kind of different terminology or different use of the same term, but it amounts to the same thing. You got this thing called a leak, and what it means is your program's going to get bigger and bigger and bigger, and eventually go bang because you ran out.
Yeah, that is weird that they're both leaks. It's like having a leak where water is staying inside where it belongs or something. I can't
Right.
Can't remember.
I think you can even use a leak for something, I would say, even more mundane, which is that let's say your program is doing some, maybe it's tracing itself. Maybe it's working on distributed tracing, and it's got some big long-lived request, and maybe the request is working perfectly well, but maybe the way that you've implemented your tracing machine is that it just keeps adding little lists, and eventually it's going to want to publish that list somewhere. But what if that list never really ends? So, I mean, it's not exactly a leak because, we have a reference to this big list of events or something like that. But we just haven't thought about changing our program to stop allocating when something happens a little bit of a longer lived fashion than we were expecting. I would categorize that as a leak, even though it's not really lost memory. Unbounded, unexpected growth. Seems like a leak to me.
Yeah, right. It could be completely valid code, and all your tests pass and everything's okay, but just because of the particular situation, it keeps growing forever. Yeah, I can see that. Well,
So
go
go
on,
on.
Brian. No, sorry.
I just wanted to add one more thing about the leaking situation. That how do you figure out where your leaks are coming from? Is a big question. And Go has a memory profiler, which is really nice. Nice GUI, and bring it up in your web browser and so on. Read up on that. But what the profiler will tell you is where the memory was allocated. What you really need to know is where is this pointer that's keeping it alive. And I know Jordan's been doing some work on tooling to try and figure that out.
Yeah, so it certainly wasn't just me. There was a program called Viewcore that's existed for quite some time that lives inside of a kind of Xdebug package or something like that in the Go library world, maintained by and created by somebody at Google. But it's kind of rotted several times because it has this weird property, which is that it's got to precisely mimic all of the internal structures of the Go garbage collector. And if it gets anything even subtly wrong, it just won't work, and it'll be just completely broken in ways that are impossible to understand. For example, something that I looked at fixing, and I have a patch for, haven't merged it yet, but there is a patch on my fork on GitHub, is they changed the meaning of this bitmap. Like there's some bitmap somewhere inside of the Go allocator garbage collector world that says, which object is alive in this chunk of objects, basically. And they switched it so that instead of having, I might be getting the details wrong, but it's something like, instead of just having one bit per object, they switched it so that every other bit was an object. And then Viewcore was not updated to have that change. So of course, maybe you could run it and it would kind of work, but the results would be complete nonsense. Anyway, so it's a little bit unmaintained. I have some patches that I think do get it back to a maintained state. And what does it do, by the way? I have been sort of just blathering about stuff without explaining what this thing does. It's a really cool tool. If you take a core dump of your Go program, so that's what happens if you send a signal to a killing signal to this to your program, Linux will dump a big file that contains all of the program's memory, all of it, just exactly how it was in memory. And so you can theoretically be the Go garbage collector. You can do that algorithm that Brian mentioned, where you find all the roots of the program, all the vars, all the finalizers, and all the stack variables, and follow all the pointers down to figure out which of the objects that are alive and which of the objects that are dead. And crucially, since you know the layout of those objects based on dwarf information, which is this whole other thing, right? Inside of a binary, it's going to tell you what the layout of objects are. Since you know all that information, you can actually figure out all of the pointers from an object to its children, to the things that it's referencing, as well as by doing a whole other graph algorithm, you can figure out the things that are pointing to an object, that's like the holy grail information, right? So it's like, let's say you have some big object that you can't collect for whatever reason. You want to know what is that object and what are the things pointing at it. And so this is what you can kind of do with a tool like Viewcore. There's all sorts of neat things, like it's got a couple of different commands you can run on it and stuff like that. I probably don't want to go through all of them, but it's really neat, and you should check it out. Yeah. I will mention one last thing here on Viewcore, which is that if you're feeling really ambitious and you want to really blow everybody's minds in the Go community, in the Java world, you don't have to run this algorithm on a dead core file. You can actually run it on a live program using this completely insane technology that this company called YourKit made. You sort of attach this little agent to your Java program, and it can figure out the reachability map and all of those things that I just described on a live Java program. And that really saved my butt several times at the last company that I worked at that used Java. And gosh, if something like that existed for Go, it would absolutely change the game completely for any Go program that uses significant or complex memory models.
Oh, that sounds awesome. We should put a link to that project in the show notes, so check them out there. Well, I'm afraid it's that time again. It's time for Unpopular Opinions. Unpopular Opinions.
I actually think you should probably leave.
Unpopular opinion. Who's gonna tell us our first unpopular opinion today?
Well, I brought one.
Let's have it, Brian.
and it's not about Go. I think all the ones about Go have been taken.
Yeah, on Reddit. On Hacker News, yeah. By Mark
So I
Bates.
thought, my unpopular opinion is I want in a chat program like Slack, say, they added threads, so you can take a message and sort of start a thread of conversation from that message.
Yeah.
So I want to be able to take something that's on a thread and make another thread. I want threads of threads.
Yeah. That is unpopular. To be honest.
That's an unpopular one. Oh yeah.
Unpopular because there's already some people that, like, I know in the Go Slack, they discourage the use of threads because they're not very accessible for like screen readers and things like that.
To use.
That's
so
like
hard
meta,
to use.
isn't it? They
It's
should
so
call them
meta.
Go routines.
Yeah. It's so meta though, that idea.
Like,
so you mean like on a tangent, you go off on a tangent and then you go off on another tangent?
Exactly. That is. I really want.
I feel like this is basically Twitter threads where they can do that, and it's awful sometimes.
They have that on Reddit too, right? You can have the whole tree of threads. I like this for the record. I think that this is a great idea, and I will subscribe to it.
The UI needs to be different though, doesn't it? Like, you know what I mean? I think that if you have a different UI, that model of conversation I think could exist. It probably needs to be a VR world where you can sort of navigate through 3D space and time, fourth dimension. So that's a good one though. We haven't had an unpopular one about Slack before, I don't think.
I mean, we've had people say they don't like Slack, but that's probably the extent.
That's not unpopular, is it?
No, that's probably.
I feel like that's a 50-50 one. It's just about half of the people like Slack and half the people don't like Slack. Brian, I think your idea, it's also kind of like, it sounds like a work of complex literary fiction. You know, sometimes you get one of those books where there's a big footnote, and then inside of that footnote, there's actually several other footnotes.
Yeah.
It's kind of like, the James Joyce of tech or something like that.
Yeah, amazing. Well, I like that one. Yeah. I mean, I don't like it to vote for it. We're going to put these on Twitter, of course. Follow us on @GoTimeFM. I think the @ is optional. I don't know. Try both. Okay. Do we have any other unpopular opinions?
Yeah, I've got one. I don't know exactly how unpopular this is these days, but I switched to using Windows for my stuff.
Right.
And I know that's crazy to some extent, but it's also kind of great because they got this thing called WSL2 now, which is like the Windows subsystem for Linux. And it's actually awesome. It's like you can do all the Linuxy stuff that you want to be doing, you know, run your compilers and your top and your whatever it is that you like to use Linux for. But then you don't have to have the pain of dealing with, you know, the year of the Linux GUI, which I hear is still this year, right? Maybe next year. I'm not sure. And I don't know. I actually kind of like Windows. So that's my unpopular opinion.
Yeah. Wow. Okay. Is that like some kind of VM thing, or does it run natively in some way?
I think that WSL2, the magic of it is that it is sort of native to some extent. It's like it's more of a hypervisor kind of technology. I'm probably using all the wrong words than a VM. But I don't really know. All I know is that it's quite fast.
Yeah. Okay.
Like,
you don't notice any problems with it.
Exactly.
I really like the technology they're doing for that because I feel like there's a ton of people that just use Windows from gaming or other stuff, and it's great to make programming more accessible. But it's so hard for me to switch back when I'm like used to certain keyboard shortcuts and things like that just aren't there. Like in Mac, I can hit Control A and go to like the start of a line, and like that doesn't work in Windows, and it drives me insane every time.
Yeah, I had to contend with that one too. But I what I ended up doing is using, what is that program called? Auto Hotkey, that lets you just go completely buck wild and do all sorts of insane things with keyboard shortcuts. So I spent like a solid couple of weeks just tweaking Auto Hotkey, and now I have like this like, you know, sort of customized machine of my dreams.
Nice. And it only took 2 weeks.
And he's going to go to his like somebody else's computer, and they're like, "Show me how you do that." And he's going to be like, "I can't use this computer right now."
I can't use any other computer now. It's been so long, I've now forgotten how to use it. Yeah, that's the danger, isn't it? I got recently one of those ergonomic keyboards that's kind of split into two. And it is quite weird to use because I'm not used to it. But I started to get kind of familiar with it. And then I went to a laptop and I was just like, I really need to cut this laptop in two, ideally, and see if I can get away with that. Just stretch it out to the same shape.
You try that and let us know how it goes.
Yeah, okay. Have you got a laptop I could borrow? Well,
I mean,
I'll
it
use
kind of
one of
reminds
mine.
me of people who use those different keyboard layouts. Like, what's the other one aside from QWERTY?
Yeah, I don't know.
Dvorak.
Dvorak. Yeah, like I had a friend in college who used that, and every time he'd like try to do something on somebody else's computer, it was always fun to watch him type because it
Yeah.
would take him like a minute to be like, I can't do this. This is so hard.
Yeah, there's a French keyboard layout as well where it's basically QWERTY except the M is just in a different place. It's just like, that's that's trolling at that point, surely.
I used to sit next to a guy called Adam who had no writing on the keycaps. Very
Really?
very minimalist
Very cool.
keyboard.
Yeah, very cool. Was his typos all the time though? He was great at passwords. He was great at thinking of passwords. Oh wow. Oh yeah. Okay. What about you, John? Have you got any specific tech that you wouldn't do without?
That I couldn't do without.
Yeah, or wouldn't?
I'm sure I have some, but it's hard to say. It's kind of like when you like reset your phone and like install it fresh,
Yeah.
and you don't know exactly what apps you had until you go to like click and you're like, it's not there. Okay, I know what app I'm missing.
Yeah, I know. I always think that when on Star Trek they go to an alien ship and they're like, "Oh, I think this is the navigation control. Can you make it work?" Yeah, okay, yeah, I think so. What do you mean? I can't even use Android. You can't get to an alien's ship and just be like, "Yeah, no probs." Beep. You know what I mean?
I mean, they're optimistic,
Yeah,
especially because phones are a lot less fatal if you mess them up.
Depends what you're doing, doesn't it?
I've never done anything on my phone that was fatal. I'll say that.
Congratulations. Okay. Any other unpopular opinions? I think we're done, aren't we? With unpopular opinions.
Just brought the one.
Oh, that's good. I just wanted to be sure in case John had one.
I'm sure this is going to be a popular one, but I love that this show has like this game show component. It's amazing. It's really fun. Having a blast.
Yeah, good. We did actually do an actual game show once as part of GopherCon, one of the GopherCons. And it was great. We got actual contestants and we had questions and they had points. Yeah, we'll definitely do that again. Maybe we'll save it for some special event like the 200th Go Time episode, which I guess will be happening this year, maybe. So that would be cool.
I think that's like very soon, like within an episode or two.
Oh, what is it? We should do a special show on the 200th. Don't you think, John?
Yeah.
Now, so I'm checking.
Yeah, sure. No problems. Do that.
This is
do that now.
194.
Do it now while we're broadcasting live.
Exactly. This is 194. So anybody who's listening, you've got 6 more episodes. Or
6 more
I guess 5 more than the 6th one will be the 200th.
Couldn't be simpler. Thank you, John.
Nope.
Well, that's all the time we have for today. Unfortunately, I feel like there's so much more we could talk about on this subject. Maybe we'll do a follow-up episode sometime. Brian, thank you so much. Jordan, a pleasure. And of course, John Calhoun. Thanks everyone for listening, and we'll see you next time.
Bye.
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 And no one noticed. That'll do. Brilliant. Thank you so much. We're still live and we're still recording, but now the podcast's over. So anything you say now that's good.
This is just for the live audience, right? This is like extra special bonus content for those people watching now.
Unless it's good enough to get stuck in the final episode.
That's true. They do sometimes take it and put it back. I forgot about that.
It's a lot of
Sometimes
pressure.
the tangents at the end allow people to or they're like, oh, we should have talked about this, and they'll stick it in.
Yeah, it happens in like it happens in meetings and stuff as well. You go to a meeting and then after it you think, oh, I should have said those words instead, but it's too late.
No, it's all right if you're the person who writes the minutes. You can just put it in.
Yeah, full control really if you're the one. But the victor writes the history, so yeah, the person who takes the minutes really could be anything going on. That happened once in a meeting where a dragon came in. I remember, and someone was, flew off on it. That was just a joke about minutes being untrustworthy sources of information.
I see.
Yeah, I sometimes say that, like, oh, it's a joke, and people say, well, it wasn't funny. But it's still a joke. It's still a joke, though.
It was a joke. I think I just didn't get it, and now I feel a little like I should have gotten it. It's more like on me at this point,
No, you're basically feeling like the average person listening to Matt's jokes.
Yeah. Oof. No, that's true. I like that. That's fine. Yeah.
We just give Matt a hard time.
I have there's people that listen that they sort of egg me on to say like nonsense things sometimes, and sometimes give in to that. That's what's happening here. So I've been hacked, essentially. The show's been hacked.
Mentally hacked.
Yeah, basically, yeah. Oh, we never even got. Oh, yeah, so much to talk about on that subject. It's really.
Yeah, it was a good lot of things. It's so hard to make sure that the audience will have the context to talk about something. I feel like most of the time when I talk about these issues, it's because we've like gone really, really deep on a particular problem, and everyone's like really glued in to what's going on. And then talking about it in general, yeah, I mean, you need that introduction. I think you guys did a really good job of the top-down basics.
I think so. I think what's nice though is sometimes there's more technical or more advanced conversations. Being around those is actually good, and people will go off and research stuff, and I think that's also nice. I like to do. We did a whole episode on defer, which is a great episode. It was like right in on, because it was just as they did the performance enhancements. I love the bit about the bits changing as well, Jordan. That was great.
Oh
yeah. I just love stuff like that. What I think we could do is like a detective show. Like now, try and go and find out who's changed that and why. Do you know what I mean? And then circle back.
I mean, that's how I had to. That's what I had to do to fix the thing. It was.
Is what you did.
It was pretty painful, but I learned a lot.
Is there any way to generate that thing from the code rather than having to sort of read the code manually? Would there be any way to generate, like, do you know what I mean?
I think it would be really, really hard. I'm sure that the minds who work on this would have a better opinion than me, but my uninformed opinion is that, gosh, I mean, the data structures that are used and the code that is used to walk them, and like all of the subtle stuff and the way that it interacts with code generation, by the way, it's really important that it interacts perfectly with the code generation. And that's just, I mean, it's just a lot of different moving pieces. The linker has to be involved. It would be tough. I don't know what to say. Maybe that's like, it's like what Dwarf wants to be, right? In Dwarf's wildest dreams, it's this thing that you emit and it's perfect and all the information is there. But as everybody knows who's tried to work on Dwarf, that's really, really tough for various reasons.
And then the other thing is, why isn't like an index of that information maintained as it goes? Like, is that just would that just be too expensive, or do you know what I mean? Like.
Well, I kind of figure that the people who did the work on the compiler and runtime probably would have been 2 extra days or something to fix up the Viewcore program, as opposed to.
I definitely think that's. I can imagine that being the case, where if it was something where they set aside some time, if you're updating one to update the other, that it would be a trivial thing, because it wouldn't be detective work. It would be like, I changed this because of this. Now I'm going to change this because of this.
Yeah, I think that's exactly right. I had this really nice email conversation with some of the folks who worked on this, and I think they just forgot that it existed, basically, because it's not really part of the main releasable artifact that is part of the Go language. And I think it should be. I mean, I think that Viewcore should be one of these essential tools in our tool belts. And I think ideally, bandwidth constraints aside, it really should be one of these first class artifacts that we can all depend on.
Is it the CMD package, debug CMD Viewcore? That one?
Yeah. I was like, what is the CMD acronym? Yeah,
Command,
exactly.
sorry.
That's right.
What are you saying? Do you
It's a
just
command.
pronounce it as command?
I guess I feel like I've never read that out loud, but yeah.
Yeah. I know, yeah. Something, I find myself saying all kinds of things that I've never actually said before. It's actually weird doing the podcast with people's names. It's very easy, often read names and then you have to pronounce them. But yeah, luckily they're sometimes easy as well. Like this is quite an easy show for me. So it's good. Okay, well, we should say goodbye to our live audience. They still were eavesdropping there. Not eavesdropping, it's an after show party. It's not much of a party, is it?
I think it's a party.
Yeah, it was. Yeah. Brian's got a drink.
I am. Yeah, it is a slight cheat though. This is alcohol-free beer.
Oh yeah, that's all right.
Yeah, that
I
counts.
think is the
It
good
counts.
choice.
It's festive.
It's
I'm drinking
alcohol-free beer, but he puts vodka in it. What's that? Drink here tea.
Drink herb tea. I like to drink water out of this bottle that says drink herb tea on it in case you wanted to know how festive I get.
Oh, yeah. Well, I mean, insubordination to a bottle is quite a flex. Yeah, nice one. John, what do you drink, mate?
I've got water right now.
It always backfires when I try and do this with John. You never let.
Sorry. I had tea earlier, but it's gone.
Another one
Not
from
much
the
to tell you.
detective show. Find out where is John's tea gone, and we trace it right to the ocean. Beautiful. Okay, well, that really is the end of the episode before one of us gets cancelled. So, thank you again for joining us, everyone, and we'll see you next time. Okay.
Bye.
I think, do I just end the call now?
Yeah,
John?
no, don't end the call. Stop
just
going
stop.
live.
Okay.